Alrighty. Hi everyone. My name is Jack, and I am super excited to finally be sharing this robot that I've been building for the last, I don't know how many months now. What is it? Quite simply, it is a robot that tracks light. So you can see here that if I cover its eyes, it's trying to track the window over there. But there are a couple of things that make this really special. First of all, this big black panel you can see at the front, that's a solar panel. So this whole thing is solar powered. And it turns on quite early in the day, about 8 in the morning normally it turns on, depends on how sunny it is. And it'll go all day until a couple hours after the sun goes down. The second thing that makes it quite special is that all of the circuitry is all analog. So there are no microcontrollers of any kind. It's all very simple analog logic, I guess you'd call it. And also, if I just get the robot to face over this way for a second with the flashlight, you'll see that everything back here is all freeform. So it's all built up out of those discrete components connected with brass wire. And I think there's about 2 meters of brass wire back there. So I think before I go and explain how everything works and how it's all built up, I'd like to quickly talk about what all these LEDs mean around the side. So the top two up here are just when the robot's on. This blue LED is always on. They're quite dim because I need to conserve power because the solar panel is relatively small and I want to work indoors. So power is a big concern throughout this entire build. So then this blue LED here is only flashing every now and then. So that's much brighter than this dim LED, but it's not on all the time. So again, power considerations. This yellow LED over here is just telling me what mode the solar logic is in, because there's 2 modes that the solar logic can be in. This LED that's not on up here is the overvoltage protection LED. So when the circuit is in overvoltage protection mode, that LED turns on bright red. These 3 down here are to indicate the state of the audio processing. So you can see I have a little brass microphone here, and when I talk close to the robot, you'll see that green LED is flashing, and that's every time it hears something, that green LED will flash. And this pink LED here, this hexagonal pink LED, is the dance flashing LED. So you'll see in a moment when the robot dances, that LED starts flashing. And these 4 on the sides are little photodiodes, and that are the robot's eyes. So to get the robot to dance, all I have to do is give it a couple of whistles. And it goes off dancing. So you'll see there that green LED was flashing every time it heard a whistle, and then it does a little dance for you. So the reason I had to do a cut there to show you the dancing is because this red LED there, I hope you can see that, indicates that the audio processing has been locked out. So it takes 3 whistles to get this robot to dance, but after it dances, it locks itself out for about 20 minutes. Again, just to conserve power because it takes a lot of energy to do that dancing. Now the last thing I wanted to show off is this glass bell jar I have for him, which I think makes him look really cool, but I don't think it comes out as well on video, so I just left it off for the beginning here. Alright, so let's have a look at the circuit now. I have a lot to say about this circuit, so I hope I don't miss anything, and I expect this is going to go for quite a while. In any case, I have taken the robot off of the base, and I have disconnected the motors here, because I noticed, it's easier to show you this way, but also I noticed that those LEDs were not very visible in the first few clips. So here are the LEDs, you can see, very colorful. But yeah, they're not very bright, and again, that's just power considerations. So I've got them all running through 100 kilo ohm current limiting resistors actually, so they're all only running on like 20 to 30 microamps, so not very much power at all. And we'll actually go through the power that each of these circuits takes as we go along, and I'll kind of give you some idea of what sort of current each section uses and the current that the solar panel outputs. In any case, this is the entire circuit. I never did get a chance to draw it up properly, so hand-drawn it's going to have to be. Just very broadly, we can split this circuit up into 3 sections. So at the top here, we have all of the solar logic and the the capacitor charging and everything. I also have the overvoltage protection down here. That should most logically it should be up here, but that's where it fit on the schematic. Then we have the motor logic here. It's actually really simple. And then this is the audio processing and the amplification and such, and then the motor oscillation. So that's like charging, motor, audio. Starting with the solar charging modules, I guess everything kind of starts with that solar panel. And that's because I wanted this to work indoors and throughout the entire day. And if you've played with solar panels, you'll know that as soon as you take them out of direct sunlight, their efficacy drops significantly. So the datasheet was actually giving numbers of, in general, you can expect 100 times less current out of these panels when they are used indoors. But that brings me to the next point. These solar panels, this is really the only reason that this project is even possible, is these solar panels. And they're monocrystalline panels, and they're actually designed to be able to be used indoors, which is quite rare for monocrystalline and polycrystalline panels. Normally you're limited to using amorphous cells, which are not as powerful. In any case, very happy to have found those on DigiKey, and it worked great for this project. So looking at this first section, this is the solar logic, I guess I'll call it. And by splitting a trace at the back of the solar panel, we can essentially split the panel into two separate panels. And by doing this, that allows me to use some clever circuitry to run the panels either in parallel or in series when this MOSFET gets closed. So in general, they are run through these two Schottky diodes in parallel, but when a certain voltage is reached, it trips this MOSFET or turns on this MOSFET, and then these two panels run in series. And this essentially creates a really, really rudimentary maximum power point tracking circuit. So when the voltage on the cells is quite low, I can run the two cells in parallel, so there's a smaller maximum power point voltage and more current flowing into the capacitors. And then once the capacitor voltage reaches a certain threshold, which I can set with this trim potentiometer here, then we can swap into series mode and we can get more power into the capacitors that way. I think it's a really elegant circuit, and a lot of these circuits were designed or based on designs by a guy who created a lot of these in the very early 2000s. His name was Wilf Richter. Oh god, I'm not pronouncing that right, am I? I've never said his name out loud before. His name is Wilf. And the whole movement back in the early 90s, late 90s, early 2000s, was called the beam robotics movement. So if you want to look into more of this, it's beam robotics, and that guy's name was Wilf, who created a lot of these circuits. Yeah, I guess we'll move on then. So looking at the next section, this was my solution for charging. So I've got a small 100 microfarad capacitor there, and that's just because I noticed that because we can kind of shut off this 7.5 microfarad capacitor and this 330 millifarad capacitor, under the right circumstances, this solar logic was getting quite unhappy, not having any load on the output. So I just put 100 microfarad there to kind of smooth everything out, if that makes sense. In any case, these are actual storage capacitors, and we have a 7.5 farad supercapacitor here, and a 330 millifarad, and you can see them both here. That's the 330 and the 7.5 farad. And you'll notice I'm being quite careful, and I've taken off my ring, and that's because even these small supercapacitors can output quite a lot of power, so careful not to short them out too much. Getting back to the circuit, by default, this solar panel, like I'll call it a smart panel, that's what I've called it. The smart panel charges up the 330 millifarad capacitor. Only once a certain threshold voltage is reached do we start charging the 7.5 farad capacitor. And I'll get back to that in a second. In any case, this here is what we call in the beam world a solar engine. And solar engines are ubiquitous across a lot of solar-powered beam circuits. And this is because, again, you don't get very much power out of a solar panel. So in order to keep everything working, the general idea is to charge up some kind of storage. So in this case, we have these two supercapacitors. Charge it up until a certain voltage is reached, and only then do we turn on the rest of the circuit and start using up that power. The way I have it set up now, once this turns on, often it'll be on for the rest of the day. And generally, these solar engines are only used to output a very short burst of power. So you'll be charging our capacitor and then dump it all through a motor in a couple of, milliseconds or a second or so. That's generally how they are used. This here is what Wilf referred to as a dual slope sampling solar engine, and is specifically designed for robots like this, where the solar engine is on for most of the time instead of only for a split second. And so the problem with normal solar engines is that they use a lot of power when they're on, or more than we would like. So the way that this circuit gets around that is, and you'd really have to go really deep into what's happening here to understand how everything's working. But this whole section here, is a oscillator. And pretty much what is happening here is, for most of the time, this node is high, and it stays high, and only for a very short amount of time does it go low, and that is the sampling pulse. So only, I forget, I was playing around with this also long ago. I forget the exact timings, but it's only on for a couple of, I don't know how long it's on for, but not very long, and it stays off for about 5 seconds, I think, every time. In any case, once a threshold voltage has been reached, in this case about 3.5 volts, then it triggers the rest of these outputs. So then it latches on. And only once the voltage on this circuit reaches a low threshold voltage, in this case about 2.5 volts, does this whole circuit turn off again. Now, the output of this solar engine does quite a lot for the controlling of the rest of the circuit. So first of all, a little bit inconsequential, but it turns on that blue LED and the LED flashing circuit. As well, it turns on the charging for the 7.5 farad capacitor through a MOSFET. And both the MOSFETs I picked here were quite expensive MOSFETs with a really low RDS on. And honestly, I think it was kind of unnecessary in the end, but it's nice to know that I'm not wasting power in these MOSFETs. And the last thing it does here, you'll see that I use it as the microphone circuit negative power supply, because this microphone circuit really shouldn't be using that much power, so I'm happy just to use it to turn on the entirety of the microphone circuit. So we're kind of getting to the end of this charging stuff now, but I'd like to kind of explain what's going on here. So like I said, in general, we are charging up this 330 millifarad capacitor, and only once a certain threshold voltage is reached do we start charging the 7.5 farad capacitor. And the effect of that is that very early in the day, when there is not much sun, we're kind of just, we charge up this 330 millifarad capacitor only, because it's going to charge a lot quicker. And it's not very much power, but we can use that power to then turn the robot to face towards the sun. So as soon as that 3.5 volt threshold is reached, the rest of the circuit is turned on, and the bot turns towards the sun. At that point, the 7.5 farad starts charging, and that's where we're charging up like our main storage. So this 330 millifarad is just to kind of get it started at the beginning of the day. So in general, it's going to fully charge and discharge this 330 millifarad capacitor maybe like 4 or 5 times before it gets enough charge to charge up this 7.5 farad capacitor. And if you kind of been listening to the amount of current and looking at that 7.5 farad capacitor, you might be thinking, there's no way that's enough current to have charged up a 7.5 farad capacitor in that amount of time. And you're right, but what's happening here is that overnight, so this circuit turns off at about 2.5 volts, and overnight, these storage capacitors are only discharging through like their leakage resistance. So by the morning, generally the 7.5 farad capacitor is still at about 2.3, 2.4 volts. So you really don't lose much overnight, and you've only got to get that little bit further up before we can start operating essentially just on that 7.5 farad capacitor. Finally, overvoltage protection. I'm really not too happy with this circuit. It's very dependent on like the component values, like these transistor gains. So you can see there, I've guessed like a 1 to 10k resistor you're going to need there for tuning the circuit. And indeed, I did have to tune that resistance quite a bit in order to get something that works. But it does work, and it works really well. In fact, the entire overvoltage protection turns on really sharply at like within about 100 millivolts, and then discharges. So it just connects straight to here and discharges the storage capacitors through a 2-watt resistor here, through another MOSFET. And I guess it was kind of a blessing in disguise, because it forced me to use these discrete components and create a very simple circuit that I wouldn't have otherwise, because I kind of forgot to design the circuit in the first place, and then I was forced to do something like this. I didn't remember that overvoltage was going to be this hard, even though I've run into this problem in previous circuits. Just gone back and looked at my notes to see if there's anything I missed about the solar circuitry, and I think there are 2 more things I wanted to mention. First of all, again, this is designed by Wilf, and it's a really, really cool circuit, like that dual slope sampling circuit. It's really nice, but I hate it. So everything here, because it's analog, it's super finicky and really hard to get working right. So it took a lot of prototyping to try and find the correct values. And then even after putting it together with those prototype values, some of these resistor values had to be changed because it just wasn't working. Because everything, again, is so sensitive. Nothing's robust. Everything's really finicky to get working. And this is the worst of them. That dual slope sampling solar engine. It's so dependent on these component values to get those thresholds right. But it does work. So it's a really cool circuit, but you're definitely going to have to play around with it. These values are not going to be the same for you. The other thing I wanted to say was the current draw. So you can see there I've written 1 to 200 microamps, and it's really hard to measure currents for these circuits because they they use such low current and for such short amount of time. So you kind of have to estimate. Well, this is the only way I could find to get these current draws is to estimate it by how fast it discharged a storage capacitor. So kind of like see how fast the storage capacitor discharges normally, then see how fast it discharges when it's connected to your circuit, and from there you can figure out the current draw. So I've written down here 1 to 200 microamps. I think that is when the circuit is in standby. So when everything is enabled, it uses 1 to 200 microamps. And you'll see that all of these current values, they all have 2 values. And that is because when the circuit is at about 3.5 volts, each of these circuits uses much less current. And once you get to that 5 volt range, the current used shoots up quite drastically. So that's why there are 2 values there. Again, I forget, but I think that when when the dual slope sampling solar engine, tongue twister, when that was off, so not enabled, then I think it was using in the order of like 50 microamps. So very low current for this dual slope sampling solar engine. So I think that about covers everything I wanted to say about the solar and the charging circuitry. I would very much like to point out where these actually live on the robot. It's very confusing, I think, to look at all this circuitry. So I am writing up an instructable with photos on every step, so like how I built pretty much every connection I have a photo of. It's still very confusing though, so just be warned. But it does go into a little more detail about all of this freeforming. In any case, this right here is this section. So that's the like the solar logic I've been calling it, and that's the MOSFET that switches the panels between series and parallel, and a little trim pot to adjust the level at which that happens. A little amber LED to tell me whether these panels are in series or in parallel. Right here we have the overvoltage protection, and you can see that 2-watt resistor in there, I think, and again the MOSFET to turn that on and off, and a red LED that turns on full brightness when overvoltage has been reached, I guess. Here are the 2 main storage capacitors. Obviously, we have the 7.5 farad capacitor, and down in there we have that 330 millifarad capacitor, and that there is the MOSFET for switching that 7.5 farad capacitor into the circuit. And then here we have the dual slope sampling solar engine. So the IC it's built around is all of these inverters, and for all of these inverter ICs, you're going to want to use HC chips. So 74HC240 is this one, and that's because other styles of 74 series chip their threshold voltage is going to be at 2.5 volts, whereas the HC chips, the threshold voltage is always roughly halfway between your supply voltage and ground, which works perfectly for this, where we want it to be operating like 3.5 to 5 volts. In any case, the rest of the circuitry is built up around that. You can see the outputs coming out here, so that turns on the MOSFET. This enables the motor controls, or the power smart heads, and this is the negative supply for all of the audio circuitry. And then again, just some LEDs. I think that brings us to looking at the motor control, or the power smart head. Again, designed by Wilf, again, super elegant. In fact, it's really crazy how simple this is. It's a little bit hard to understand. If you do have some idea about like control and electrical design, I guess the best way to explain this is it's a PWM-based P controller with a massive deadband. So it's just got proportional control, and the reason it doesn't oscillate all the time is you've just got a massive deadband in the middle. And I'll try and explain this as succinctly as I can. So here we have a photodiode bridge that influences our oscillators, and those are like the eyes of the circuit. And here we have we have an oscillator here. If we get rid of these 2 components, pretty much all we have is a CMOS oscillator. And if we were to output that straight into these 2 inverters here, and I've actually got 3 inverters stacked up, and that is just to provide enough power to the motors, because each one can't really output very much current. I think 20 milliamps is the max, so this allows more current to be output to the motors. In any case, ignoring these 2 components, this is pretty much just like, I guess you would call it a reversible P controller. So you've got some kind of wave whose duty cycle can be influenced completely by these 2 photodiodes. You've either got it fully on or fully off, and everywhere in between. This RC pair here creates that deadband. So it creates like a low pass filter where the output here has to be on for a certain amount of time before, or on or off for a certain amount of time before it actually flips this inverter. So that creates that deadband in the middle. I hope that's clear enough. I don't expect it to be that clear, but again, it's a really super elegant and super simple circuit. We have two other ways of biasing these this oscillator here, or I guess biasing the entire circuit now that I'm looking at it. This motor dance like input here comes from one of the oscillators on the output that we'll look at later, and that just holds the inputs high and low to make the entire circuit turn left and right. And these two here are these two micro switches at the top and bottom. So that's just used for the up and down movement, and that's just to make sure that, because left and right you can spin infinitely, but up and down I wanted to put in some kind of limit switch to make sure it doesn't over travel. And then we've just got some 10K resistors here to make sure that if both the switches miraculously were pressed at the same time, we're not like discharging the capacitor straight through these tiny limit switches. All right. Again, looking at where that is on the circuit, that is these two ICs here, one for up and one for up, down, and one for left and right. Most of the circuitry, again, it's really simple. Most of the circuitry is just at the very top of each of these ICs here. And the rest of it is just connecting all of the extra inverters together to output to the motors. And the motors connect the inverters here. We also have the photodiodes. So this was, I was really silly and I put these photodiodes on last. So you can see I have some really windy connections to connect them both together. And then I have to connect those through actually I think in the end I used a 1 mega ohm resistor to connect it to the actual power smart head. I guess I will speak briefly on this resistor here. That is like a sensitivity resistor, so it influences how sensitive these photodiodes are in influencing the rest of the circuit. Again, I said I've gone to a 1 mega ohm, and I actually tried to push it even further. I wanted it to be even less sensitive because it was oscillating at the end. I guess I'll actually probably talk about this later when we get to tuning, but just know that that was the sensitivity resistor, and I've got it at 1 mega ohm now. Again, talking about power requirements, I've got here 0.5 to 1 milliamp. So these power smart heads use most of the power in this circuit. And that is when they are like locked onto a light source, I'll say, when they're in standby. So not when the motors are actually moving. Each of the motors uses about 20 to 40 milliamps, depending on what voltage the capacitors are at and how fast it's all moving or changing speeds. So when it's dancing, we're using a lot of power, like I haven't actually measured it, but I guess when it's dancing, you're going to be using it in the order of 80 to 100 milliamps. Again, just gives you some idea of how long everything can last. Finally, we have all the audio processing and the dancing circuitry. Starting with the audio processing, again, this entire circuit was designed by Wilf and just adjusted by me. He called these beam sonics because the idea was that you would have a lot of these robots chirping and listening to each other chirping and triggering each other. But I've just got it tuned to trigger off like my own whistles. Starting up here, we have a microphone, and I found this really cool brass microphone, which worked perfectly with the rest of the aesthetic of the robot. And we've just got two like preamplifiers. That then goes into this circuitry. And again, it's pretty simple, but probably not at first glance. All it is like this circuitry here is making sure that your whistles are the correct length and there's enough time between each pulse. So it's not listening for just random noises. It really needs to be 3 distinct pulses of the correct length with the correct distance between them. You'll notice that often when I was demonstrating, I didn't need 3 distinct pulses, and that's because everything's quite leaky. So you'll see in the next part why that's a problem, but I actually kind of like it. In any case, ignoring all of this, what we're looking at here is, I guess you would call it a charge pump. So every time one of those whistles makes it through this check, it pumps, I guess, from this 1 microfarad capacitor into this 3.3 microfarad capacitor. And that's what counts for those 3 pulses, is pumping a little bit of charge into that 3.3 microfarad capacitor. This is essentially just a monostable circuit. So once it reaches that trigger, it'll start discharging through this 1 mega ohm. So that sets like how long it's dancing for. And then resets the whole circuit once that 3.3 microfarad has been discharged. And like I said, everything's quite leaky here with all these diodes for stopping current flow everywhere. So at a high voltage, especially, the leakage is quite significant, and this will actually trigger randomly. or just from like a single noise it'll trigger. And I quite like that because it means the robot's a little more dynamic. In any case, this output then goes to the dance enable. I guess I'll call that dance enable net, but that's just turning on the dance oscillators. And it also triggers this next monostable circuit. And this just has, I've used a 100 microfarad and a 10 megohm resistor there to create a really long time constant. And that's what locks out this circuit and locks it out for about 20 minutes, I would say. Again, it depends on how leaky everything is being. I don't think that this is the best arrangement for all these inverters, but based on, I played around with this quite a lot to try and get this working with only 6 inverters, and I think I actually got it in a way that's pretty reasonable. But if you do want to have a look at the circuit and try and make it better, make it less leaky and everything, be my guest. I'm sure it can be done. But with 6 inverters, this was the best I could come up with. So then, yeah, that dance enable then enables that final HC240 chip, and that just has 3 oscillators on it. So 3 really simple, just CMOS oscillators, and 2 of them are used to bias that motor control, and 1 of them is just used to flash that pink hexagonal LED. Yeah, I think that about covers the circuit. So we'll have a look at where that sits on the freeforming. By the end of it, I was running out of space. I knew that there were a lot of components here, but I kind of just ignored it until the very end. So a lot of this is very packed. Here are the preamplifiers. This is all that like processing circuitry, and this is the oscillators here. And then again, just a trim pot to tune how sensitive the microphone is. I guess also important is these 3 LEDs. So that one, like I said in the beginning, the red LED is to signify that the whole circuit's been locked out. This yellow LED doesn't do very much. It just flashes once when the circuit triggers. I just left it in there, kind of for visual symmetry. I think in the end this turned out looking quite pleasing. And then that green LED, like you saw, is every time it hears a sound, that green LED flashes. Yeah, I think that about covers the circuitry. I've definitely forgotten something, so I'll try and think about that. Yes, so the last thing I forgot to talk about was the current draw for this audio processing. I played around quite a bit with the component values for these resistors here, trying to get it to use much less power, and I ended up with a circuit that consumes about 300 to 600 microamps, so quite low, but I wish it was lower. Most of that is in those preamplifiers there. So all up, I think in general this circuit uses about 2 milliamps when it's on standby, and again 20 to 40 milliamps when it's moving, and like 80 milliamps max when everything is moving at the same time. The solar panels indoors, on a dark day, I'm guessing they'd probably output about 200 microamps, so not very much, or probably 200 to 500 microamps. When it's facing away from the sun on a dark day, you're getting almost nothing. You'd be getting like in the 10 microamp sort of range. On a bright day, when it's indoors and just facing in a random direction, I'd guess you'd probably get like 500 microamps-ish. And when it's facing directly toward the sun, indoors, and on a bright day, that's when I'm getting, like maximum 5 to 10 milliamps. So on a dark day, the circuit really doesn't turn on. So on like really cloudy days, it turns on in the morning, looks around a bit, but it can't stay on. Most days though, it'll turn on, like I said, at about 8, it turns on and starts looking for the sun. By midday, most days, it is fully charged and it's working exactly as expected for the rest of the day. And then after the sun goes down, so my window is actually on the east that the robot looks out for most of the day. So the sun kind of disappears at about 6 in the afternoon, and by 8, most nights, it's off completely. But sometimes, depending on how much it's looking around at the end, and if it dances a lot at the end, it can last a lot longer than that, and it can last a lot shorter than that. All very dependent on the sun and how much it's moving about. Just to give you some idea of how long everything works and the currents that everything consumes. The last thing I want to mention while I've got this all apart is the mechanical design. So you can see the solar panel rests in this brass frame here, and the frame actually comes apart. So this side of the frame comes off, and the whole panel can slide out. I'm not going to slide it out now, because it actually ended up being a lot more tight in there than I initially expected. So you can see I've had to drill these 2 holes in the side. So in case I ever do need to take this panel out again, I need to push it out with a skewer there to start with, because it's much tighter than I expected. And the reason I did this, it was a lot of effort to get these, to get all this, to fit right, exactly how I want. Like you can see from the front, There are very few gaps in the joints, or for all being done by hand. And the reason I did this is because I wanted to solder a lot to the frame, and I didn't want to burn the solar panel while doing that. So that's what I did there. Um, these motors, these N20 motors I call them, they were actually a terrible choice for this. I went with them because they're ubiquitous, and in case I ever do need to replace them, 10 years down the track, I hope I'll be able to find the same ones again. But they have a lot of backlash in the gears, and they're a little bit noisy. That doesn't bother me too much, but the backlash made this a real problem to tune, because the head is so heavy, it has a lot of like inertia. It was oscillating like crazy because it would stop and then the head would continue turning thanks to the backlash and the weight of the head, and then it would have to turn back and have to turn back. So it was really hard because with tuning the sensitivity of the circuit, there are I think three things that are a problem. You have like the sensitivity of each photodiode, you have the speed that everything turns, and how big that deadband is. So you have to kind of balance those three things to get a robot that is sensitive enough, but doesn't oscillate. So my robot was oscillating a lot, even in like not very bright lights. Even still, it oscillates a lot if you take it outside. Indoors, it's pretty okay unless it's in direct sunlight. So originally I tried, like I was talking about a long time ago now, I originally tried to minimize the sensitivity by increasing those R-sense resistors here to like over 1 megohm. But anything over 1 megohm and the whole circuit stopped. It was just way too much resistance between the photodiode bridge and the motors. So that was a no-go. I also tried to adjust the deadband of this circuit, but I really didn't like that either because, okay, so this brings me to another problem with these power smart heads, is these inverters are not meant to be driving massive loads like a motor here. So they can't turn on very quickly. Even with three of them in parallel, they can't turn on very quickly. So while I say I'm using PWM to drive these motors, the frequency of that PWM is in the tens to hundreds of hertz. Again, I forget exactly, but it's really slow. So instead of being like nice smooth PWM, it's really jerky PWM. It's not PWM. So it jerks instead of like smoothly turning. So I really didn't want to increase this deadband even more, because then that initial jerk is even larger. So increasing the deadband was a no-go. Trying to decrease the sensitivity with a resistor there was a no-go, and the backlash I can't really solve. So the only thing I could do was put these caps over the photodiode. So I've drilled some small holes in some brass, held it all together with some clear heat shrink, and I don't particularly like this solution, but it works now and it's okay. I think the funniest thing is that if I had chosen really like bad quality photodiodes, I think this would have worked well. The only reason I had such an issue is because you can see these photodiodes, the sensitive area is so massive. So they're like really sensitive photodiodes. I chose them just for the look. I didn't even consider this to be a problem. I really liked how that looked, and then they ended up being way too sensitive, and I couldn't make them less sensitive. So just some things to think about if you attempt something similar. The robot is going to want to oscillate in bright sunlight, and you're balancing sensitivity, the speed that everything moves. Oh man, yeah, I forgot about the speed of the motors. So you're balancing the speed of the motors, the backlash, the deadband, and the sensitivity. It's a really hard balance to try and get something that works indoors, works outdoors, and doesn't oscillate.